I've been building a JavaScript library that lets people type math on the web. This is an example of how it works. It's similar to tools like MathQuill, but mine's going to be better. This is the representation that I've been showing so far. So in these videos, I've been talking about this token representation, which is sort of just a flat list of characters until you need the nested structure. So if you have a fraction, okay, we're splitting that up into a numerator and a denominator. But for the most part, if you type something flat, it's just a flat representation, which is very useful to have for editing operations like inserting or deleting a character. But when you try to actually do something with this, like make a graph or evaluate what they typed as an actual math object, this is really not helpful, right? We need to be able to parse it into something better. And so, as indicated by the super sneaky question marks, which we can remove now, I've been building something, which is a parser. So if you type 2x plus 1, that gets parsed into this representation over here. Instead of viewing it as just the four characters, 2x plus 1, we are viewing it as addition. And inside the addition, we're adding together two things. We're adding together multiplication of 2 times x plus that decimal 1. So this is how a mathematician would think about what you've typed, as opposed to how a input would think about what you've typed. And this is really important to include in the input library, because sometimes the parsed information is going to get fed back into our rendering of the input. So for example, if you type f of x equals x plus 1, you don't want this behavior always, but it should certainly be possible to do things like syntax highlighting, where we actually look at the fact that, okay, you're defining a function, your argument is x, and now in the body of the function you're using the variable x, or even if you have a more complicated multivariable function, we should be able to do this kind of thing. And if we have the parsed representation and it's part of our process, then we can. So part of building a math input is doing the parsing. So I built a parser and I had 3 design goals. The big design goal was modularity, because what I'm doing with my math input is making everything modular and everything customizable so that you, as a developer, as a user of the library, could add new functionality. So why does that matter? Well, sometimes you need just very basic functionality. Like if I'm building a math something for elementary school, I might only need the ability for users to type in decimal numbers and fractions, and maybe a mixed number that's like a whole number and a fraction. And that's all I need. And so I should be able to strip away a whole bunch of the functionality and just have those types of tokens and that kind of parsing. On the other hand, if I'm building something for calculus, I might want to add a whole bunch of features, right? All these new kinds of tokens and all these new kinds of structures, and then I need all the parsing to go along with it. So obviously you could just have options for this to turn things on and off. An even better example is, this is sort of a warning story of why it's important to let developers add their own types of features that you didn't think of. So Desmos, which everyone has used, is based on MathQuill, another open source math input library. MathQuill does not have support for matrices. So if you want to type a matrix, too bad, you just can't. And MathQuill is not modular, and so Desmos was not able to add matrices into their core product. They had to create a whole separate matrix calculator that didn't rely on MathQuill in quite the same way. So this is an example of how it could go wrong if it's not modular. And then, you could make the argument of, well, MathQuill should have just included the matrices in the default product. Why does it have to be modular or customizable? Well, sometimes you should be able to define something totally custom, like this, right? Emoji math like this probably shouldn't be included in the default parser, because this isn't really default normal math behavior. But you should absolutely be able to do this if you want to as a developer. There are good pedagogical reasons to make something like this, and you should have the option to add it. So as much as you can dream up, you should be able to add it into the input, and that includes being able to customize the parser and add new kinds of things that can be parsed. Goal number 2, graceful error handling. This is just important for the user experience. If a kid types something wrong or makes a mistake, we should be able to sort of constrain the error, and so parse all the things that are correct. And then in the one place where something is wrong, we should be able to explain exactly what happened with a clear error message. Final goal is really more of a priority thing. We're going to care more about the developer experience than about hyper efficient algorithms. The developer experience is really the thing that matters, and speed and efficiency is not that big a deal when what you're parsing is this long. It just doesn't matter that much. So developer experience is where it's at. All right, so I built this parser and I did make it modular. So let's talk about how it works, and let's talk about how you could use this parser and customize it and add your own little modules. So almost all kinds of parsing essentially look like Pac-Man, where you're chomping some tokens or you're eating up some parts of the input one at a time, left to right. Well, with modular parsing, we are going to have a bunch of individual parselets, and each one knows how to chomp certain things. So for example, a decimal parselet knows how to chomp, 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 but it only eats decimal numbers. So it looks for digits, maybe a decimal point somewhere, and that's all it knows how to do. If it runs into anything else, it's going to give up and throw an error. The variable parselet only knows how to eat variables, and so on. And so the big idea is that the overall parser is just going to go through and try these parselets one at a time. And so I will provide all of these and more by default, but you can add your own parselets, and the parser will go and try those as well. So yours are like a first-class citizen, right? To show you an example of what a parselet actually looks like, they're very, very simple to write. This is the variable parselet, right? This is the one that's actually going to work when we consume the letter y. So the very first line of the parselet says parser.consume, which is basically the Pac-Man chomp. We're going to consume a token, and it turns out to be the letter y. And parselets just assume that everything is awesome, but they make an assertion and say, it better be the case that the token I just consumed, in this case, was a letter. And if not, throw an error. So in this case, we consumed a y, which is great. And so then it can return a variable node. That's the output, right? I know that this is a variable. You have a variable y. I just parsed it for you. If you try a parselet and it consumes something that's not correct, it's going to throw that error, and the overall parser will just try again with a different parselet. So we've successfully consumed the variable y. Now we're going to chomp down again, but because we have this y on the left-hand side, we're now looking at some different categories, things like infix parselets. So infix is an operator that has something on the left and the right, like adding. We have something now on the left, and so we can start to look at these, or look at the postfix parselets like factorial, where that exclamation point goes after something that already exists. So we have a left-hand side. We'll try a bunch of things. We try adding, that's going to throw an error. Try subtracting, throws an error. Once we get to the equation parselet, which looks like this, it's going to be wonderful. So the equation parselet consumes a token, which means it chomps down on the equal sign. It says that better have been an equal sign, and it was, so we keep going. Now this is fun. Each parselet has the option to throw back to the main parser and say, hey, go get me a right-hand side, right? Go parse the rest of whatever is here, so the 2 times x minus 5, and figure out what that is and give it to me, and then I will make you an equation using the left side and the right side. So these parselets are very simple to write. And that's because it's so modular. This is based on what's called a Pratt parser. And the idea is a programmer writing a parselet doesn't have to be concerned with what the other parselets are doing. Just focus on your thing. So you just consume tokens until you're done. And if you hit something unexpected, throw an error. And that's it. Of course, in the real world, there are a few ways in which the parselets have to talk to each other. So there are 2 simple communication hatches. One is the fact that the order of operations can be specified. So if you type 1 plus 2 times 3, it's really important that we parse that as 1 plus 2 times 3, not 1 plus 2 times 3, right? You have to parse it correctly. And so we can define the order of operations by just setting up all our parselets in order, where the top is things that bind really tightly and stick together. At the bottom is things that are sort of last in PEMDAS, for example. We set this up within the individual parselet. You don't have to think or care about order of operations at all. Just parse your thing, and that's it. There's one other communication hatch for more complicated situations. I'll give you an example. One complicated situation I dealt with was the adjacent multiplication parselet. Adjacent multiplication is when you have two things side by side. So like 2x should be parsed as multiplication, 2 times x. There are situations where you want to be cautious about that, such as x minus y. You could reasonably parse the x as a variable x, and then minus y as negative y. And it's possible that the adjacent multiplication parselet could interpret this as x times negative y. And we could go into the adjacent multiplication parselet and like hard code in that if it's a negative on the right, that doesn't work. However, you as the developer should also be able to add your own parselets. And if we're trying to be modular, we need you to be able to communicate information to the adjacent multiplication parselet yourself as well with your new types that you're adding. And so instead of hard coding it in, we have this tagging system where the adjacent multiplication parselet has a little bit of code where it creates its own special tag that you can use. And then the negative node imports that tag and uses it and says, look, hey, I cannot be on the right side of adjacent multiplication. If you have a negative node, that's not going to go on the right. And so then the adjacent multiplication parselet sees that tag and acts accordingly. And this tagging system is so simple, and I have found it to be able to solve quite elegantly every problem that I've run into so far. So this is the only other escape hatch we need. So you have this modular system, and as a result, a whole bunch of tricky things just work. This idea that if one parselet fails, we rewind, like unconsume tokens and try another, that just works for you. You don't have to worry about it. Order of operations. When you're writing a parselet, you don't have to worry about it. Juxtaposition, this idea of like side-by-side things, and the idea that we should be able to parse if two things are adjacent to each other without any token in between. Writing a juxtaposition parselet is super easy. Behind the scenes, that was kind of a lot of work to make that effective. For you, the developer writing a parselet, you don't have to think about it. And then the error messages. This system makes it very straightforward to generate quite good error messages. And so that works as well. So really, I am very proud of this system. I feel really good about it. And this is one of the huge sort of key milestone steps in building this math input. So I'd love your feedback, but I feel great about it, and we're on to the next thing.